All right, let's dive into one of the biggest, most famous puzzles in all of physics, but we're going to look at it from a totally new angle. It all comes down to a simple analogy about hitting a moving target. And trust me, this little idea, it might just change how you see, well, pretty much everything. So, let's talk about the Michelson-Morley experiment. For decades, this thing was like a ghost haunting the halls of physics. Its result was just baffling. It made absolutely no sense to anyone. But here's the big question. What if the experiment wasn't a failure at all? What if everyone was just looking at the blueprints upside down?
Okay, so picture this. It's the late 1800s, and physicists are convinced space is filled with this invisible stuff they call the luminiferous ether. They figured light must travel through it, kind of like sound travels through air. Now, if that's true, then as the Earth zooms through this ether, the speed of light should look a little different depending on which way you're looking. So they built this incredible device, the interferometer, specifically to measure that tiny, tiny difference. And the result? Nothing. Zilch. Nada. No matter which way they pointed it, no matter how many times they ran the test, the speed of light was stubbornly, bizarrely, the same in every single direction. To the scientists of the day, this was a massive, colossal failure. But that failure was the very first clue that would lead us to Einstein's theory of relativity. So you have to ask yourself, why did it fail? Or maybe the better question is, did it?
To really get what's happening here, we need to put the whole ether idea on a shelf for a second. Instead, I want you to think like a sniper, or, maybe an old-world cannon operator. The concept is called deviation shooting, or, put more simply, leading your target. The logic is super simple, right? If you aim a cannonball directly at a moving ship, you're going to miss every time. The shot lands where the ship was. To actually hit it, you have to aim where the ship will be when the cannonball gets there. You have to lead the target. And believe it or not, this is the exact same problem the Michelson-Morley experiment was facing, even if they didn't quite realize it at the time. Here, the cannonball is a beam of light, and the moving ship, that's a mirror, hurtling through space on this big rock we call Earth. So the question becomes, how do you aim? As it turns out, there are basically 3 different ways you could think about this problem. 3 different ways to aim, and each one is built on a completely different assumption about how reality itself actually works. Okay, let's break these down. Step 1 is easy. If the mirror's not moving, you aim right at it. Simple. Step 2 is our sniper logic. You calculate the mirror's future position and you aim for that spot. That feels intuitive, right? But then there's step 3. And this is where things get a little mind-bending. Step 3 says you can't just aim for a future position. You have to aim for a future event. That one unique combination of coordinates and time where the light beam and the moving mirror can actually intersect, given that light speed is absolute. And this right here is the critical point. The argument is that the original experiment was unconsciously designed using step 2 logic. They just assumed they could calculate a future spot, aim there, and the light would hit. But is that really a safe assumption when you're dealing with something as fundamental as the constant speed of light? Well, the great thing is we don't have to guess. We can actually build a simulation, plug in the laws of physics, and see exactly what happens. And our source material did exactly that, using Python to model the precise coordinates and timing of the light beam. So, according to that simple, intuitive step 2 plan, if you've got a mirror 10 units away moving at a certain speed, you do the math, and you expect the light to arrive at a nice, clean time. That time would be exactly 10. A perfect round number. It's the neat and tidy answer you'd write down on a physics test before Einstein came along. It's the blueprint. But reality isn't that simple. When you run a simulation that has to obey that one unbreakable rule, that the speed of light is constant for everyone, it turns out the light in the mirror cannot meet at t equals 10. The geometry of the situation just doesn't work. The actual event, the real intersection of their paths in space-time, has to happen at a slightly different moment. The simulation shows the meeting actually happens at t equals 10.05038. Now, that might seem like a tiny difference, but in physics, that tiny difference is everything. It's the gap between our intuition and reality. The universe doesn't care about our planned location. It only cares about a real event that's physically possible. So here's the crucial part. For the full round trip, the experiment's blueprint was based on an expected return time of exactly 20. But the simulation, which models reality, shows the actual return time is 20.10076. See the problem? The experiment was built to detect a timing shift, but it was starting from the wrong baseline. It was based on a flawed blueprint.
And this brings us right back to that famous failure. These numbers from the simulation, they reveal that the entire design of the experiment was based on a flawed assumption about how to aim at a moving target in our universe.
The experiment was built using step 2 logic, aiming for a pre-calculated future spot, but the universe operates on step 3 logic. In the real world, light and matter can only interact at a valid future event, a specific point in space-time that respects the constant speed of light.
So the experiment didn't fail at all. It actually worked perfectly. It produced a null result because the effect they were looking for, an effect based on a flawed step 2 model of reality, simply doesn't exist. The experiment correctly reported that their blueprint for the universe was wrong.
Now, this insight doesn't just solve a 19th century puzzle. It points to a really radical idea about reality itself, a concept the source material calls information lag. Information lag is this idea that we never see a direct snapshot of the present moment. Instead, what we think of as our reality is a reconstruction, a picture our brain assembles from bits of information that are all arriving at different times from different places. We are always, quite literally, living in the past.
So what does this all mean? Well, it means the speed of light isn't just a cosmic speed limit. It's the actual rule book for how information about events is structured. From this point of view, time doesn't physically slow down when you're moving fast. Instead, your reconstruction of events just gets rearranged by the geometry of the information you receive. So all those weird effects of relativity, like warped spacetime, they might not be reality itself bending, but just the natural outcome of this information lag.
And that leaves us with a final provocative thought. Is reality itself actually bending and stretching the way we've always been told? Or are we simply observers, running on a slight delay, trying to make sense of a picture that's assembled from light that's always playing catch-up? It's a question that reframes one of the greatest discoveries in science, not as a story about a warped reality, but as a story about the fundamental geometry of how we know anything at all.